Project management. Basically, we will be talking here on how to manage a certain project. One example is to construct this bridge. Another example is to construct a building. And of course, we can apply project management also in doing some research. So when we construct a bridges or let's say a building, definitely we will be having our estimated time in order to complete our project. By using project management or by applying project management in a certain project, we can estimate the time or expected time to complete our project. Now, project scheduling involves sequencing and allotting time to all project activities. Managers decide how long each activity will complete or will take and compute how many people and materials will be needed at each stage of production. So, of course, when we have our project, we consider the people and then the materials that is needed to, again, to complete the project. One popular project scheduling approach is the Gantt chart. So we have here our example of a Gantt chart. We have the task name, first planning, research, design, implementation, and then follow-ups. So this is just an example of a Gantt chart. And then during the first quarter of 2019, we have planning starts from January 19 and will end up to March 19. So this is just an example. And then in doing research, research will start from February 19 to March 19. And then design will start from March 19 to April 19. And then implementation start from April 19 and then to July 19. And of course, the follow-up is June 19 to July 19. This is just an example of a Gantt chart. So again, that is for project scheduling. Now, project controlling. So another part of project management is project controlling. The control of large projects, like the control of any management system, involves close monitoring of resources, cost, quality, and budget. Of course, these are important in having a project because of course you need the resources and of course the cost and budget. Now, to help the managers in scheduling, monitor, and control large and complex projects, we have here what we call as PERT, or the Project Evaluation and Review Technique, and CPM, the Critical Path Method, were both developed. So, PERT, or Program Evaluation and Review Technique, this is used to examine the tasks that are in a schedule and determine a variation of the critical path method. It analyzes the time required to complete each task and its associated dependencies to determine the minimum time to complete a project. So basically, uh, we will be using PERT in order to estimate the time to complete the project. Later on, I will be discussing on how to use PERT, or the Program Evaluation and Review Technique. Now, the framework of PERT and CPM, take note, PERT is Project Evaluation and Review Technique and CPM is the Critical Path Method. We will be applying this one to estimate the completion time of a certain project. First is to define the project and prepare the work breakdown structure. So of course, we have to determine what is the project or what will be our project. And then develop the relationships among the activities, So we have to determine what are the different activities that is being involved in the project, and then decide which activities must precede and which must follow others. So example, activity A, activity B, and then activity C. So if we say B will start if activity A is finished, so we have to decide that. and then draw the network connecting all the activities. So we will draw a network. That means we will be using, in my discussion, we will be using a circle, and then it will be connected by an arrow. So uh, by connecting different circles with an arrow, we form what we call as the network. So draw the network connecting all the activities and then assign time and or cost estimates to each activity. So in our example, we will be using time. And then compute the longest time path through the network. This is called the critical path. So actually, this will cause a delay. So that is why it is called as a critical path. So we have to compute the longest time path through the network. And then lastly, use the network to help plan, schedule, monitor, and control the project. So these are the framework of PERT and CPM. PERT and CPM is important because they can help answer the following questions. 1. When will the entire project be completed? So basically, if you are a manager, then you will be estimating on the completion of the project. So that will answer this question, when will the entire project be completed? Another question is, what are the critical activities or tasks in the project? That is, which activities will delay the entire project if they are late? So, uh, in our computation later on, we will determine the critical path method so that we can identify which activities will delay the entire project. So, that is for question number 2. That is why we have what we call as the critical path method. Number 3, which are the non-critical activities, the one that can run late without delaying the project's completion. So again, we can determine the time for that particular activities. And also, what is the probability that the project will be completed by a specific date? So, probability will also be discussed for our project. At any particular date, is the project or on schedule, behind schedule, or ahead of schedule? So, there might be a question later on that uh, uh, oh, is it possible to end up the project on this date, on this month, on this year, later on? Okay, so that question will be answered by PERT-CPM. Are there enough resources available to finish the project on time? Of course, this is part of the analysis. So all of these questions can be answered later on in our PERT or Program Evaluation and Review Technique. Now in doing PERT and CPM, we have here the network diagrams and approaches. So in our computation, we will be using network diagrams. Two approaches for drawing a project network. First, we have what we call as the activity on node or AON. Nodes designate activities. So we have here our node. Okay. We use a circle for our node, and then our activity is within our circle. Activity A, activity B, and then activity C. We have here an arrow connecting our node. So we call this one as a network. And then another approach is the activity on arrow or AOA. So arrows designate activities. So we have this one as an example of an AOA. This is our activity which is in an arrow. That is why we have here activity on arrow. So arrow designates activities. A comes before B, and then which comes before C. Okay? In other words, we have to finish first the activity A before B will start, and then finish first activity B before C will start. So again, these are the two approaches for drawing a project network. We have the AON or the activity on node and the AOA or the activity on arrow. So we will be using, probably we will be using activity on node when we compute problems involving PERT or project evaluation and review technique. Okay, now in our discussion with PERT, we have here our example. Milwaukee Paper Manufacturing Incorporated, located near downtown Milwaukee, has long been trying to avoid the expense of installing air pollution control equipment in its facility. The Environmental Protection Agency has recently given the manufacturer 16 weeks to install a complex air filter system. Milwaukee Paper has been warned that it may be forced to close the facility unless the device is installed in the allotted period. Johnny Stenberg, the plant manager, wants to make sure that the installation of the filtering system progresses smoothly and on time. Table A below shows 8 activities that need to be performed in order for the project to be completed. So we have here the list of activity designated by letters A, B, C, D, E, F, G, H. So for this activity, you have here the description. Activity A, you have here build internal components. For B, we have to modify roof and floor. C, construction collection stock. D, pour concrete and install frame. And then E, build high temperature burner. F, install pollution control system. Install air pollution device for activity G. And inspect and test for H. So these are the complete project. I mean, the activities, these are the different activities in order to complete the project. Now take note for A or activity A, there is no immediate predecessors. For activity B, again, there is no immediate predecessors. For activity C, we have here our immediate predecessors, which is A. In other words, C will not start unless you have finished activity A. And then also, activity D could not be started if you will not finish activity A and B. And of course, for activity E, its immediate predecessors is C as well as in F. We have here C. And for G, immediate predecessors is D and E. And for H is F, G. So again, in other words, for this G and H, you cannot start G if you are not finished with activity D and E. Okay, so additional information for the project is this one. For table B, time to finish for each activity. For activity A, you have 2 weeks to finish. Activity B, we have 3 weeks to finish. Activity C, we have 2 weeks to finish. For D, we have 4 weeks to finish. E, we have 4 weeks to finish. F, we have 3. G, and then H. If you sum up all of these weeks, we have 5, 6, 7, plus 4, 11, 15, 16, 17, 18, 19, 20, 25 weeks if you sum up this one. But in PERT, we can have our estimation for this time. Now, table C, this is an additional information for our problem. Okay, so time C, this is time estimates for Milwaukee Paper project. So this is just an estimate. Okay, we have what we call as the optimistic time A, which represented by small letter A, most likely time, which is represented by small letter M, and then pessimistic time, which is represented by small letter B. So the optimistic time for A, we have here 1. Is optimistic time for B, we have here 2, 1, 2, 1, 1, 3, 1 for the succeeding activity. For the most likely time, we have this one, and then for the pessimistic time, we have this one. Now, if you have noticed, Okay, so we rearrange this one in a horizontal form, but later on we will arrange this one in a vertical form. So we have here our question to that particular problem. First, we have to draw the AON network for Milwaukee paper. And then second, we have to draw the complete AOA project network. AOA is arrow, activity on arrow. And then AON is activity on network, node. Okay? Activity on node, activity on arrow. The third question is calculate the earliest start and earliest finish times for the activities in the project. Number 4 is to calculate the latest start and finish times for each activity in the project. Number 5, calculate the slack for the activities in the project. Number 6, identify the critical path and find the project completion time. And lastly, find the probability that the project will be finished on or before the 16-week deadline. So we have here 7 questions. And when we solve this one, I will break this one. Okay. I will break these questions as I will group these questions as 1 and 2. And then group 3, 4, 5, and 6. And then we have group 7. Find the probability that the project will be finished on or before the 16-week deadline. In other words, I will be uh, regrouping these questions into 3 groups. First group is question 1 and 2. Second group is questions 3, 4, 5, 6. And then uh, the last group is for question number 7. Here is the computation for the Milwaukee Paper Manufacturing Incorporated. We have our list of activities A, B, C, D, E, F, G, H, and then we have here the immediate predecessors. So for question 1 and 2, we have to draw the AON or the activity on network, activity on node network for Milwaukee paper. And then number 2 is to draw the complete AOA or activity on arrow project network. So we will start first with the AON. So activity on node. So we have here, sorry for that. So we have AON. I will write here AON, or that is for activity on node. So we will have here our starting point. So we will write here start. So we have here a circle. This is our node. And then for activity A and B, there is no immediate immediate predecessor, so we will write here A, and then we write here B. Okay. So I will write here an arrow connecting to A and then connecting to B. Actually, you need not to draw this one. You can also draw directly A and B only. Okay. So I will write here. Let's say I will write. Okay. Let's say we need not to write this part or draw this part. Okay. But for our purpose of doing an example, I will just write there start. Okay. But this is not counted. Okay. So, and then we have here for C, this is an activity after A. Okay. So after A, you have here C. I will draw here C. Activity C. Okay, I will write here an arrow. So that is activity C. And then we have activity D, that is A and B. So A and B, I will write here D, activity D. I will draw here an arrow from A and B connecting to D. That means you cannot start activity D if A and B is not yet finished. Okay. And then next is E, that is after C, as well as E is after C. So I will draw here after C is E. Okay, E. I will draw here E. Same with F, that is after C. So I will draw here after C. We have your F and then activity E. So you have here an arrow connecting to E and F. Then next to that is G, which is after D and E. So D and E, after D and E, we have G. So I will draw here G. And then I will connect here E and D. Okay, so E and D, these are activities before G, D and E. So immediate predecessors for G, we have D and E. And then for H, we have here F and G. Is our F and G, so I will draw here H, activity H. So we have here an arrow connecting to H. So this is our activity on node. We have our activity in node, okay? And then we have here an arrow connecting those activities. So we call this one as a network of activities. So we have done with question number 1. Draw the AON network for Milwaukee paper. This is the AON network. Okay. This time we will draw the complete AOA project network. So AOA. AOA. Activity on arrow. So that is for AOA. So, okay. Take note, A and B. Okay, A and B. Again, there is no immediate predecessors. So I will have here. Again, we have our start. So I will write here start in our AON. So I will write here as 1 as our start. Okay, and then you have here an activity A on arrow, activity B on arrow, activity A on arrow. Okay, then we have here next activity is C, that is after C is after A. So after A we have here C, arrow C. Okay, so let's say we call this one as 4. And then A, B, C, D, that is A and B. So if you have noticed A and B, this is arrow A, arrow B. So we only have one arrow for each activity. So we will have this one as okay, 5, activity D. Now you cannot do this one connecting here 2. If you will connect 2 to 5, then take note we only have one arrow for activity D. We will not write here D. If you write here D, then you have here a duplicate of your activity. So we did not write that part as D and then arrow. So we will erase this one. Okay, sorry for that. So we have this one. Okay. In this case, A and B, we have to draw a line here. I mean not line but an arrow. This is a broken arrow. We have this one. We call this one as, okay, I will change it. I will change the color. We call this one arrow as a dummy activity. Okay, dummy activity. Dummy activity. We call this line as our dummy activity. So dummy, that means empty. Okay, so that is why we will draw a broken line. We need not to draw this broken line of your arrow from 2 to 5, because if you draw it from 2 to 5, that means you are connecting to the next activity. But for this case, this dummy arrow or dummy activity will be connected to point 3, because these are activities that is done before you will start activity D. Okay, so that is your uh, A and B. We have here A and B. Now next for C, D, E. E is after C. Okay, E is after C. So after C, we have here E. For after C, so we will just pattern this one. After, sorry for that. We have here C, A, B, C, D, E. Okay, so 1, 2, 3, 4, 5, 6. And then we also have here E. And then F is after C also. So we will draw F here. I mean, that is not the case, but we have this one. Number 7. This is F. Okay. E, F. And then G, we have D and E. Now, D and E is after, G is after D and E. This one is D and E. So, if this is D and E, that is after that we have G. So, there must be an arrow here for your G. Okay. If we will connect here to this one, then we will have another activity. If we will connect this one, so we will now change our E to this part. Okay, we will change our E to this one. That means if you have your activity G, you have to finish first activity D and E. D and E. Okay, so we will have here. Okay, after that FG, we have here H. So this is our F, G, and then we have our H. So this time we have to connect. We have to have only one arrow for H. Then we have here our end point. So for this case, if you have noticed our F, if we will connect F to this one, then we will go directly with our F here as well as our G here. So we have to change that one. F, G. We have to change those line or arrow by this one. Okay. This is our F, this is our G. So 1, 2, 3, 4, 5, 6, and then we end up to 7. So if you have noticed, this is our arrow, A, B, and then C, D, E, F, G, H. So this is our AOA network. Okay, so if you have noticed, or if you have observed, in our AOA, it is much complicated when compared to AON. The simplest way to draw your diagram is based on AON. We have this one, AON. Okay, now we will proceed with the next questions. The next questions we have calculate the earliest start and earliest finish times for the activities in the project. Another one we have calculate the latest start and finish times for each activity in the project, and then calculate the slack for the activities in the project, and then identify the critical path and find the project completion time. Okay, so to answer these questions, we will base it in table B. Table B contains time to finish each activity. We have activity A, activity B, and then we have here our activities in terms of weeks. Okay, so we're talking here about the earliest start, earliest finish times for the activities, and then latest start and finish times, or latest start, latest finish. Okay, and then of course we will calculate the slack, and then identify the critical path and find the project completion time. So allow me to discuss first what is earliest start and earliest finish time. So I have to draw this one. Okay, let me draw this circle. Okay, we will be using this circle later on. Okay. Now, we have here our, say for example, activity A. We will write here activity A, the name of activity. And then we have here the time or the duration of your activity. Let's say 2. For activity A, we have here 2. And then for this part is our earliest start. We will call it ES. So earliest start. So earliest start. And then this part is earliest finish. EF. So we call it as earliest finish. And then this one is the latest finish, LF. We have here the latest finish. And then this one is the latest start, LS, latest start. Okay, what is this earliest start means, or ES? These are the earliest time at which an activity can start, assuming all the predecessors have been completed. For the earliest finish, so we have this one for 2. For EF, or the earliest finish, this is the earliest time at which an activity can be finished. For the latest start, we have this one, LS. This is the latest time, um, the latest time at which an activity has to finish so as not to delay the completion time of the entire project. For LF, or the latest finish, this is the latest time which an activity has to finish so as not to delay the completion time of the entire project. That is our latest finish. Okay, now when we solve this one, we will base it on our network, AON or AOA. So we will be using the activity on node. So if we go back to our previous slides, we will be using this one. So we have here BAB, CDEFGH. Okay, this is the easiest way. So we will be using this part, AON. So I will draw AON diagram from this portion. So we have here our start, AON diagram. Let's say start, and then we have here our A and B. our A and B, and then let me recall our AON 1 2 1 2 3 4. Okay, another two circle. We have here 1 and then 2. Okay, and then we have here 3. Okay, sorry for that one. Okay, and then I will have it this one. Okay, so this is our start, so let me change this one as a, sorry, I will erase this one. I will draw it again. Okay, so this is connected to A and then to B, and then let me check first. Okay, this is connected to this is connected. Okay, I will write now this one. Okay, let me draw it first. Okay, so we have here a line. Of course, this will be divided by this line. And then for A, we have here our A. And then we have here 2. For B, we have here B, and then B is 3. The duration of the activity, that is 3. And then C, we have here for C, we have 2. Okay. And then this one is for D, which is 4. Okay, there's an arrow connecting to this line, to this circle. And then we have this one. Okay, we have this arrow. And then C, this is our F, which is the duration is 3. Okay, we have here FE, this is E, wherein the duration is 4. And then we have here G, the duration for G is 5. And then we have here H, which is 2. And then we will connect our arrow to F, to E. Okay, C, E. And then this is D, G. Let me check first. D, E, G connected to G. Okay, so we have this one connected to G. We have this one connected to G. And then we have this one connected to H. Connected to H. Okay. So this is start. I will make use of S as our start. Then we have, of course, 0. Okay. So this is our AON network. We write our activity. We have here A, B, C, D, E, F, G, H. And then time, we have 2, 3, 4, 4, 3, 5, 2. Now, first is to calculate the earliest start and earliest finish. So I will change my color of pen. We have this one. So I will make it as red so that we can distinguish. Okay. Now, when we calculate the earliest start and earliest finish, we will make use of what we call as the forward pass. So we will draw here a forward, what we call as the forward pass. So color red. Okay. So this is an arrow with this direction. Forward pass, that means we start from S until the last activity. So that is what we call as forward pass. Now, in a forward pass rule, in a forward pass, this is a process that identify all the earliest time. Okay, so that is the forward pass, all the earliest time. Now, we have different rule for the forward pass. First rule is, of course, the earliest start time rule for the forward pass, earliest start time, if an activity has only a single immediate predecessor, its earliest start equals the earliest finish of the predecessors. Okay? Earliest start equals the earliest finish, if that is the activity has only a single immediate predecessors. Another one, if an activity has multiple immediate predecessor, its ES is the maximum of all EF, earliest finish values of its predecessors. So that is the rule for the forward pass. Okay, so we will start now. So this is 0, of course this is 0 because this is a starting point. For again the forward pass, all you have to do is to add the value from your ES to your duration. So 0 plus 0 equals 0. And then we will copy this 0 here, and then we will copy this 0 here. Okay, 0 plus 2, that is 2. Okay, 0 plus 2 equals 2. And then going to this part, we will copy 2. Okay, so if we will copy 2 here, whatever your value here, we just copy 2. And then 2 plus 2, that is 4. And then this 4 will be copied here. And of course, to this value E. Arrow going to F, you have your 4. Arrow from C going to E, you have here your 4. And then 4 plus 3, that is 7. And then this one, 4 plus 4, that is 8. And then 8, we will copy it here. Or since there are 2 arrows, then we will stop 8 first. We will identify what is the largest value. So we go back to B, 0 plus 3, that is 3. And then we will copy 3. Okay, try to look at this one. For letter D, you have here 2 arrows. Okay, this is 2, this is 3. So we have to select the highest value. So instead of writing 2 or 3, we will make use of 3, which is the highest value. Okay, so 3. Okay, 3 plus 4, that is 7. Okay, so this time, if you have noticed for G, we have 2 arrows or 2 activities before G. That is activity D and E. This is 8, this is 7, so we will follow 8, the highest value. 8. 8 plus 5, that is 13. Okay, if you have noticed for each, we have here 2 arrows connected to each. We have here 7 and 13. So this time, we will copy 13. Okay, and then 13 plus 2, that is equivalent to 15. Okay, so we have done with the forward pass. So we have here our earliest start and earliest finish time. We have this one in color red. Earliest, take note this one, earliest start and then earliest finish. So we have identified our earliest start and then earliest finish. Okay, so these are our answers for number 3. Earliest start for A, we have 0 and then 2. For C, we have 2 and 4 and so on. This time, we will proceed to another question. So, for question number 4, calculate the latest start and finish time. So, I will change the color of my pen. Instead of using red, I will make use of, let's say, blue. Okay. To answer number 4. Now, to answer number 4, in number 3, we have what we call this one as forward pass. So, we call this one as forward pass. Okay, our direction is going to this direction. Okay, forward pass. In forward pass, we add the activity with its duration. Okay, the time with the duration time of each activity. Okay, we add, and then if there are two arrows connecting to your activity, then we have to select the highest value. Okay, for example, this one 8 and then 7, we select 8. Okay, for the latest start and latest finish time, of course we will start at this part. If this is 15, then this will be equivalent to 15 also. Okay, so I will write here 15. This time, instead of forward pass, we go the what we call as the backward pass. Backward pass. Okay, backward pass. So, on this direction, from this activity going to this activity. So, that is backward pass. Now, in forward pass, if we add the duration and then select the highest value if we have two arrows, then this time, we will subtract the duration and select. If there are two arrows, then we will select the lowest value. Okay, if this is 15, 15 we will subtract now to this duration. 15 minus 2, that is 13. Okay, so this 13 is now copied here, and then this part is also 13. Okay, now 13 minus 5, that is equivalent to 8. 13 minus 5 is equivalent to 8. Okay, okay, 8. So 8 will be copied here from this arrow. 8, and then this one also 8. Okay, 8 minus 4, that is 4. For this part, 8 minus 4, that is also 4. Now, we go back to this one. 13 minus 3, that is 10. Now, if you have noticed to C, we have here two arrows connecting to C. So we will select either 10 or 4. So for a backward pass, we will choose the lowest value. So we will be choosing, so I will write here 10 or 4. So we will be choosing 4 for this part, the lowest value. Okay, 4 minus 2, that is 2. And then this one, okay, if you have noticed also for A, you have here 2 and 4. So of course, we will be choosing 2. Okay, 2 minus 2, that is 0. And of course, you have here later on, okay, because there are two arrows, and then 4, we will copy 4. And then 4 minus 3, that is equivalent to 1. Of course, the lowest value is 0. And then we have here 0. So, we have already calculated number 4, the latest start and finish time for each activity in the project. So, for A, our latest start and latest finish, we have here 0 and 2, respectively. For B, we have here 1 and 4, respectively. For C, we have here 2 and 4. For D, 4 and 8. F, 10, 13. For E, we have 4 and 8. For G, we have 8, 13. And for H, we have here 13 and 15. So, these are now our solution for question number 4. We have the latest start and latest finish time for each activity in the project. This time, we will calculate the slack for the activity. Okay, so we will have it here. Let me arrange first. So we have calculate the slack. Take note that our slack, when we compute our slack, I will write here our slack. Let's say slack. Okay. Our slack, when we compute our slack, that is LS minus ES. Or we have ELF minus EF. So we have to look at this one. ELS minus ES and then LF minus EF. That is how we compute our slack. So I will write a summary here. We have our activity. Let's say A, B, C, D, E, F, G, H. So we have here A, B, C, D, E, F, G, H. Okay. For our ES, for ES of A, we have ES for A, we have 0, of course, 0. 0, B, and then C, we have here 2, and then D, we have here 3. Of D, E, we have 4. F, we have 4 also. G, we have G, 8, 4 for 8, and then 13. That is for our ES. For our EF, okay, for EF, we have here our EF. For A, that is 2, 3, 4, 7. So we have here 2, 3, 4, 7. And then 7, 8, 13. I mean 8, 7, 13. EFG, 8, 7, 13. 8, 7, 13. And then 15. That is our EF. For LS, we have here our LS. LS 0, 1, 2, 4. 0, 1, 2, 4. And then EFG 4, 10, 8. 4, 10, 8. And then H we have 4, 10, 8. We have 13. 4, 10, 8. We have 13. LF, this time LF. Latest finish. So I am summarizing 3 and 4. LF, we have LF this one 2, 4, 4, 8. 2, 4, 4, 8. 2, 4, 4, 8. 8, 13, 13. 8, 13, 13. And then we have 15 for our LF. Then after LF, we have the slack. Take note, slack equals LS minus ES. LS minus ES. So we have here 0. LS minus ES, 1 minus 0, that is 1. Okay. And then this C, 2 minus 2, that is 0. 4 minus 3, that is 1. 4 minus 4, that is 0. And then 10 minus 4, that is 6. 8 minus 8, 13 minus 13, that is 0, 0. Okay. If you have noticed here, okay, the critical path for this part is If you have noticed to our slack critical path, uh, there are zeros occur here. So in our identification of a critical path, we identify 0 in our slack as our critical path. So for this one, we say yes. And then for 1, of course, no. For 0, we have here yes. No. We have here yes for 0. And then no. And then yes. Yes. That means all the zeros here. So let me change my color of pen. All the zeros here are our slacks, and then that is also our critical path. We have here 0, 0. That means our critical path, we have here A, and then we have here C, and then we also have E, and then G, H. Therefore, our critical path is A, C, E, G, H. So our critical path is from path A to C to E, and then G, and then H. Okay, if you look at this one, that is from A, C, E, G, H. So we have this one. Okay, so we have this one, and then this one. Okay, and then this one, and then this one. Okay, these are our critical path. Another way of identifying our critical is you have to count the number of arrow in connecting the two nodes. Okay, for example, A, C to F to H. So we have only 3 arrows, 1, 2, 3. And then another one from A, we have here A to D, 1, D to G, 2, and then G to H, 3. Okay, take note of the arrow direction. So we only have 3 arrows connecting from A to H. And then this one for B, 1, 2, 3. So we only have 3 arrows connecting from B to H. However, from A to this path, A to C, 1, C to E, 2, E to G3, and then G to H4. So we have 4 paths. Therefore, that is our critical path. Comparing with other paths, we only have 3 paths. So this one is 4 arrows. So that will be our critical path. So that is another way of identifying the critical path. You have to count only the arrows connected from each activity. Another way, of course, by computation, we have this one. We identify our ES, EF, LS, LF, and then the slack. For a slack value of 0, that will be considered as our activity that is found in our critical path. So all the zeros here, for activities with 0 slacks, that will be considered as our critical path. So we have already answer number 3, number 4, the earliest start and earliest finish. Then we also have calculate the slack for the activities in the project. Okay, so we have this one, the slacks. And then of course the critical path, we identify our critical path as A, C, E, G, H. And then this time, find the project completion time. Our project completion time is definitely this one, 15 weeks. Okay. The last value here will be our project completion time. Okay, so we have done with questions 1, 2, 3, 4, 5, and 6. This time we will proceed to the last question, number 7. Find the probability that the project will be finished on or before the 16-week deadline. Okay, now for this question, we will base it in our table C, the time estimates for Milwaukee paper project. So activity A, B, C, D, E, F, G, H, and then we have here the optimistic time, most likely time, and then pessimistic time. So I would like to rearrange this one, okay, to compute this problem. I will rearrange this one as, or just like this first, I mean this uh, presentation, okay. So let me arrange, okay, I will write it here. My activity, let's say activity A, B, C, D, E, F, G, H. I will just estimate the space. So these are our activity: A, B, C, D, E, F, G, H. Okay, we have our activity here. And then for the optimistic time, so I will write here OT. Okay, OT, optimistic time. I will just write here OT, optimistic time. That will be our A. So our optimistic time, we have here 1, 2, 1, 1, 2, 1, 1, 2, 1, 2, 1, 1, 3, 1, 1, 2, 1, 2, 1, 1, 3, 1. Okay, 1, 2, 1, 2, 1, 1, 3, 1, 1, 2, 1, 2, 1, 1, 3, 1. Next, most likely time, so I will write here ML. Most likely time, that is in terms of M. So 2, 3, 2, 4, 4, 2, 3, 2, 4, 4, 2, 3, 2, 4, 4, 2, 4, 2, 2, 4, 2. Okay, and then we also have our pessimistic time, that is PT. That will be our PT will be our B, our uh, literal value. I mean the denoted by B. So PT 34367 34367, and then 9113 9113. Okay, now in our computation for this part, we have what we call as the expected time. Expected time, T, we will make use of T as our expected time. That is, our formula is A plus 4M plus B all over 6. Okay, so I will write here our expected time T. Okay, so this one for A, you have here for our A, that is 1 plus 4 times, this is for A, expected time for A, 1 plus 4 times 2 plus B, that is 3 all over 6. So 4 times 2, 8, 9, 10, 11, 12 over 6. So that is 2. Okay, that is how we compute our T. Same with this one, that is 4 times 3, 12, 13, 14, 15, 16, 17, 18 divided by 6, that is 3. Okay, and then 4 times 2, 8, 9, 10, 11, 12 divided by 6, that is 2. 4 times 4, 16, 17, 18, 24 divided by 6, that is 4. Okay, and then we also have 4 times 4, 16, 17, 17 plus 7, 24, divided by 6, that is 4. And then 4 times 2, 8, 9, 9, 18, divided by 6, that is 3. 4 times 4, 16, 17, 18, 19, 20, 30, divided by 6, that is equivalent to 5. 4 times 2, 8, times plus 1, 9, 12, divided by 6, that is 2. So that is how we compute our expected time. Now this time, we will have our variance. Okay, I will have here our formula for finding the variance. So to find the variance, okay, you have our formula for finding the variance is B minus A all over 6. This is 6 raised to 2. So that when we compute the variance of A, okay, variance of A, that is B that is 3, 3 minus 1, okay, B minus A. So 3 minus 1 over 6, and then raised to 2. So 3 minus 1 equals 2 divided by 6, that is 2 divided by 6, that is 1/3. And then if we compute 1/3 raised to 2 using your calculator, so the result will be, using calculator, 0.11. So our variance here, okay, so for A, that is 0.11. Using the same process for B, our variance for B, that is again 0.11. Using the same process, all you have to do is to compute that one using same process for B. Okay, for B here, I will write variance for B, that is B minus A, 4 minus 2 over 6. Okay, raised to 2, that is 0.11. Okay, and then for letter C, the variance for letter C, okay, I have already computed C, that is 0.11. And then for variance D, that is 0.44. 0.44. And then for variance E, for E, that is 1.0. You have 7 minus 1, 6 divided by 6, that is 1. 1 times 1, that is 1. Okay, so that this one is 1.78, 1.78, and then 0.11. So let me erase this one so that I have a space. Okay, erasing this part. Now, after we computed, okay, after we computed our expected time and then the variance, we have here the variance. This time, we will now compute our what we call this one, the standard deviation, okay, or the project variance. We have our variance, then we have what we call as the project variance. Okay, so for project variance, when we compute the project variance, that is the summation. If we say summation, all you have to do is to add all the variance. So we have here the summation of the variance of activities on critical path. Okay, so variance of activities on critical path. Okay, so take note our critical path. So let us recall our variance of critical path. I mean the critical path. Our critical path is ACEGH. Okay. ACA, we have this one, CEGH. So the variance for that one is 0.11, 0.11, 1, and then 1.78.11. So all we have to do is to sum up our variances for this part. Okay, so that we have here our project variance, or we have this formula, I mean the symbol. Okay, this one. Okay, that one. So let me rewrite it. I will write it again. Project variance. Okay, so that our project variance, we have this one, which is equivalent to the sum of the variance of activities on critical path. You have 0.11 plus 0.11, and then plus 1 plus 1.78 plus 0.11. So all in all, that is equivalent to 3.11. Okay, so that is 3.11. This time, we have to identify our standard deviation, project standard deviation. So project standard deviation, we have this one, project standard deviation, as our symbol. Project standard deviation. Okay, our project standard deviation is equivalent to the square root of your project variance, this one. So square root of 3.11, that is equivalent to 1.76 weeks. So I will write it here. Okay, so I will write it here, equals 1.76. This is in terms of weeks. Okay, so we have our project standard deviation. Once we find our project standard deviation, we have what we call as the z-score. Okay, so our z-score, or the standard normal equation, we have z-score in statistics. We have here our z-score, which is equivalent to, okay, we have to determine our z-score. Now the formula for finding the z-score is equivalent to the due date minus, in statistics we use z-score. So for this case, we also use z, expected date of completion. So we have here due date minus expected date of completion. Okay, divided by, of course, our standard deviation. Project standard deviation. So we have our due date, which is 16 weeks deadline. So 16 minus our expected date, we have computed already as 15 weeks a while ago, divided by our project standard deviation, which is 1.76. So that is equivalent to 0.57. That is our Z. So once we have our Z, which is equivalent to 0.57, we have to refer it to our Z table. So we will refer this one, refer to Z table. Okay, so we have here our Z table. Okay, let me check this Z table. So I will open now my Z table. We have this one Z table. So this is Z table. Okay, this is the standard normal probabilities. So 0.57, take note, we have here our Z 0.57, 0.57. So from Z table, this is our Z, we have this one, and then we have this value. For example, this is zero point 0.5, take note 0.57. This one is zero point 0.5, and then you have to look at 0.07 here. Okay, zero point 0.5 plus 0.07, that is 0.57. So 0.5 to 0.7. So this is now our equivalent. Okay, zero point 0.5 to 0.07, that is 0.7157. This is now the probability. This is the area under the curve of a standard normal curve or standard normal distribution. The area here is 0.7157. 7157. So the area is equal to 0.7157, or if we multiplied it by 100, that is 71.57% in terms of percentage. So to answer our question, find the probability, our probability is 0.57, I mean 0.71 0.7157, or in terms of percentage, that is 71.57. This implies now that 71.57 chance there is 71.57 chance that the pollution control equipment can be put in place in the weeks or less than let's say 16. Okay, so that is how we interpret our probability. So there is a probability that, I mean, equivalent to 71.57, that the project will be finished in 16 weeks or less. At least you have that probability, 71.57%. So this is our final answer for question number 7. So take note, when we solve our probability with the project, that the project will be finished on or before 16-week deadlines, we have to compute our expected time, which can be summarized as a plus 4m plus b over 6, and then after that we compute our variance, which can be solved using the formula b minus a all over 6 and then raised to 2. So once we compute our variance and then expected time, we compute our project variance, which is the summation of the variance of activities on critical path. So we have already identified our critical path. We have A, C, E, G, H. So their variance are the following: 0.11, 0.11, and then 1, 1.78, and then 0.11. If you sum up those variance, then we find our project variance, which is equivalent to 3.11. And then after that, we have to compute the standard deviation of our project, which we take the square root of 3.11. We have 1.76 weeks. And then after this process, of course, we have to compute our Z. We have this one. To find the value of Z, we have due date minus expected date of completion over this project standard deviation, which we computed as 1.76. So our due date is 16, and then our expected date using our critical path, we have 15. So The value now is 0.57. After we find the z value, we have to refer to the z table to find the area. And that area will be our probability. Okay, so again, that is all about the project evaluation and review technique.